Hi everybody, today we're going to talk about chemical bonding, and just as a side note, it might be really wise for you to have out your periodic table, but you need a special periodic table. You want the periodic table that has electronegativity values on it. So if you'll dig that out, you can either find it in this module or you can go find it under the resources for the whole year module. We are concerned with these numbers beneath each element. This is a really special periodic table because it gives you values for each of the electronegativities that we've talked about in our unit dealing with periodic trends and that sort of thing. So these numbers underneath each atom represent the given atom's electronegativity. So we'll use this down the road during this lesson, and I just want you to have it ready to go. So let's discuss some facets of chemical bonding. A chemical bond is this attraction between two different atoms, and it is an attraction based on the valence electrons. And remember, valence electrons mean those outermost electrons, those S and P electrons that we'll talk about here in a second. And those are either going to be transferred from one atom to another, or they're going to be shared between two atoms. So if you'd like to look up a little bit more on chemical bonds after this video, you can go to the crash course video on YouTube and look up something called atomic hookups. It has another good description of different bonds and that sort of thing. And just as a terminology reminder, we talk about individual atoms being the actual elements, and they've come together to form a larger piece called a molecule. So why is it that atoms bond? Well, we're going to talk about it here, and then I'm going to show you some electron configurations that help to illustrate this a little bit further. But basically, atoms really want to be in a situation where their potential energy is minimized. Potential energy for atoms, is bad. Potential energy is like them being stressed out, right? So if you have a ton of homework while you're preparing for your soccer game and you have a musical instrument that you need to practice, that's going to be a pretty stressful situation, right? The more stress, the worse it is for you. Same deal with atoms, except we measure it in this thing called potential energy. So the more potential energy, that's bad, and atoms want to minimize that as best they can. So one way they can do that is to find themselves with a full octet. A full octet means they will have 8 of those valence electrons. And so forming bonds is one way for them to acquire 8 valence electrons. So we're going to look at a few different types of chemical bonds today: ionic, covalent, and metallic. And we'll also actually split covalent into 2 broad categories. We're going to talk about polar covalent bonds. Those are really cold. And nonpolar covalent bonds. This actually has nothing to do with temperature. It means something else, but we'll get there in a second. Okay, so let's talk about ionic bonds first, and I'd like you to write down on your note guide a really important term. This term, transfer, underline it, star it, whatever you need to do. Transfer and ionic go together. And what are we transferring? Well, we're transferring electrons. And to try to make a little bit more sense of this, I've gone ahead and I've written out the electron configurations for both sodium and fluorine, and I threw oxygen on there just for another example for us to use. So if we look at the electron configurations, and I've drawn orbital notation here, for these atoms, you'll notice, let's look at fluorine first. Fluorine is this middle orange one. You'll notice that fluorine has an empty spot right there for an electron. And so if it can get an electron in that spot, it's going to be really happy. Why is it going to be really happy? Because its valence shell, its outermost shell, is the one that has the 2s, right? 2s and 2p. You'll notice that the s sublevel always holds 2 electrons, p sublevel always holds 6 electrons. 2 plus 6 is 8. That's where we get the octet rule from. If fluorine can acquire 1 more electron, it's going to be really happy. That's why we would predict that fluorine always forms -1 ions, meaning it has gained 1 electron. Why? Because if it can always gain 1 electron, it's really happy. So fluorine doesn't always form ions, but if it does, it almost always forms a -1 ion, and we call that the fluoride ion. And you can see a similar deal going on here with oxygen. So for oxygen, oxygen has 2 spots, right? Here's its valence shell, the 2s, 2p, its outermost s and p is its valence shell, and right here, there's a spot, and right here, there's a spot, right? So that's why oxygen, again, doesn't always form ions, but if it does, it forms the oxide ion, which is O minus 2. It has room for 2 electrons. In fact, if it can gain those 2 electrons, it's going to be really satisfied. Now, it's a little bit more confusing for the metals, the things on the left-hand side of the periodic table, the things that like to lose electrons. So you might say to yourself, wait a second, the outermost energy level here in sodium is the 3, right? So theoretically there's a 3p here, there is a 3p here, and so you'd say for sodium, well, it needs to gain 7 electrons, right? It has 7 spots to fill, those 7 spots. But here's sodium's little trick, right? It can actually bypass this completely. So instead of trying to fill the third energy level, sodium is going to do this. It's going to say, if I can just get rid of this electron out of the third energy level, then this becomes my new valence shell, the second energy level. And voila, it already is full. So there's my full valence shell. I have my 8 valence electrons. I have my full octet. I'm happy. And that's why sodium almost always forms, well, it does always form +1 ions if it makes an ion, because it has 1 extra valence electron to get rid of. And so how does this relate to bonding? Well, if you look at sodium and fluorine, sodium's in the situation where it desperately wants to get rid of its 1 extra electron, right? So we've already highlighted here that sodium has this 1 extra electron, whereas fluorine has this spot for 1 extra electron, and that's represented up in this picture with this electron and this vacancy. And so if sodium and fluorine pass each other on the street, sodium's going to be all too happy to give away this electron that's just kind of out there floating, and fluorine's going to be super pumped to acquire that electron, right? So this is a mutually beneficial situation for both of them. If sodium can get rid of its electron, fluorine can then accept it. They're really happy with that situation. So this is an ionic bond whenever we transfer an electron from one atom to another. What about a covalent bond? Let's have 2 fluorine atoms next to each other, right? And as a reminder, fluorine has that 2p sublevel, right? It has a 2s that looks like this. It has a 2p sublevel that looks like this. So it has a vacancy. It has a spot right here for an extra electron. This is its valence shell. It badly wants an extra electron. So you might look at 2 fluorines and you'd say, well, okay, we're going to take this electron and we're going to give it to this fluorine, right? And then this fluorine on the right is really happy because it has 1, 2, 3, 4, 5, 6, 7, plus this 1 new electron. It has 8 valence electrons. But the problem with that is there's no way that this fluorine is going to be happy with that, right? That fluorine is 1 vacancy away, 1 electron away from having a full octet. There's no way it's getting rid of electron. It only wants to gain. So both of these atoms are really in a tough spot because they both are in a situation where they want extra electrons. So what do? Well, they work together. Instead of both kind of being greedy and saying, well, I'm just going to keep my 7, you keep your 7, and we'll find a new partner, they say, well, let's work together. What if we share these 2 valence electrons, i.e. we'll count them both as part of our octet? That means that fluorine on the left has 1, 2, 3, 4, 5, 6, plus these 2, 7, 8 valence electrons, whereas fluorine on the right has 1, 2, 3, 4, 5, 6, plus these 2, 7, 8 valence electrons. So just by sharing and working together, they end up in a situation where they both have 8 valence electrons and everyone is happy, everyone's good to go. Metallic bonds are a little bit different. We're just going to touch on them here briefly and then not really go very in-depth with them. But a metallic bond is really cool because the electrons actually don't belong to any given nucleus. They're able to move freely between the atoms. And so we actually refer to that as like a sea of electrons. And this helps to describe why metals conduct electricity, right? Because let's say you have, you have an outlet over here. So this is your outlet. Voila, there's your outlet. And you put a piece of metal in the outlet, right? So that's a really poor decision, but you somehow connect this metal to the outlet. Again, bad decision. Why is that a bad decision? Because the electrons are able to carry a charge, and they're able to carry that charge from this place over to your hand. Again, I'm a professional artist. There's your hand. They can carry the charge over to your hand, and then you can get a shock, right? So that happens because the electrons are not tied down to any one given atom, and that means sticking a fork in an outlet is a really, really terrible idea, so let's not do that. All right, let's talk about covalent bonds again, but we're going to dig down a little deeper. As we said, we're going to talk about polar covalent and nonpolar covalent, and this has to do with how much they are sharing electrons. So really big word that we want with both types of covalent. Doesn't matter whether it is polar or nonpolar. Covalent things are going to share electrons. Now, the degree to how nice they are when they share is going to dictate what type they are, but regardless, in both cases, they are sharing. So, in a non-polar covalent bond, we have a situation where electrons are shared equally. So let's imagine a situation. Let's imagine that you have a twin, right? And you and your twin, you are identical in every single way. And you're actually identical in how much you like ice cream, right? Which is shocking. I don't know how anyone could like ice cream more than me personally, so I'm not sure how this would work. But regardless, let's say that you have a twin and you both like ice cream the same amount. If there's a half gallon of ice cream left in your freezer, and let's also assume that you're, nice people, you're going to split the ice cream down the middle, right? You both like it the same amount, you're both going to get some, everyone wins, everyone's happy. Well, if atoms come together and they like not ice cream but electrons the same amount, they're going to share them equally, right? So hydrogen and another hydrogen atom, if they're both the same atom, they have to essentially like electrons the same amount, right? They're the same atom. Then they're going to share those electrons equally, and that's going to be a non-polar situation. So polar, even though we're not talking about the poles of the Earth are a pretty good example, right? So on our planet, we know that there's a North Pole and a South Pole, and they're on opposite ends. So really the term polar means opposite ends. And so when we say non-polar, we don't have essentially like a left-hand side and a right-hand side of this molecule, right? It looks the same throughout. The electrons are spread evenly throughout that molecule. But contrast that with something that looks a little bit like this. So again, as we're talking about poles, look at how on the right-hand side here, the molecule looks bigger, and on the left-hand side, it looks smaller. And it's not really smaller or bigger, but what we're showing there is the electron density. So you'll notice that fluorine has way more electron density around it than hydrogen. So why is that? This is a situation where maybe you have a twin, but you like ice cream differently for some odd reason. Maybe you both like it, but you really like it, right? So your twin is nice, and they say, well, all right, let's both have a little bit. I'll have a scoop, and you can have the rest of the half gallon, right? So you're still sharing this ice cream, but you're getting a ton of ice cream, like fluorine over here, and your twin is just getting a little bit, because that's all they really want. And so they're okay with that, and that generates something called a polar covalent bond. Now again, polar, we can think of poles of the Earth. We have a situation here where this molecule doesn't look uniform throughout. Right? There's kind of a right-hand side that has way more electron density, that's over here, and a left-hand side that has way less electron density, and that's on the left-hand side. And that's all given rise because we like electrons a different amount. So how can we predict this if we don't know how much atoms like ice cream, we don't know how much they like electrons, we can't even see these atoms, what the heck are we supposed to do? It turns out that there's a really cool value, and it tells how much atoms are able to pull electron density towards them within a covalent bond. So they're not just like grabbing electrons randomly from out in space, but if they're bonded to something, this dictates how much they pull electron density towards them. And as you remember, electronegativity in general gets higher as you go into the upper right-hand corner where fluorine, and it's really low down here by francium. So at this point, you want one of these periodic tables in front of you. Have that out as well. You want the periodic table that has those electronegativity values on it. Remember, they're the ones that are written down at the bottom. So like for fluorine, it's a 4.0. The scale for electronegativity goes from 0 to 4.0. And one little note while we're here, you'll notice the small noble gases just don't have an electronegativity because they already have a full octet. There's no reason for them to bond. They don't bond, and so they're just happy without pulling any sort of electrons towards them because they already have their full octet. So how does this come into bonding? Well, we have a little chart that you're going to want to commit to memory. So it turns out that the difference in electronegativity between atoms can be used to dictate the type of bond that happens. Let's start out with nonpolar. So what if we have a situation where everyone likes electron density equally? That's shown down here in letter A. You'll notice there aren't poles to this molecule. It looks uniform throughout. Everyone's kind of sharing the electron density equally. So that means they must like the electrons about the same. And so that means they're going to have a really small difference in how much they like those electrons. So that means if you have an electronegativity difference that's anywhere from 0 to 0.3, you're going to have a nonpolar covalent bond. Again, very small difference between the electronegativity value for both atoms. That makes a nonpolar bond. What if you have a situation where you and your twin both like ice cream, but you like it more, right? So you're both getting some, you're still sharing here, but you like the ice cream more. One atom likes the electron density more. If the difference is a little bit larger, again, this is the difference in how much these atoms like electron density. If it's between 0.4 and 1.7, that's going to be our polar covalent bond, right? So this is a situation where we are sharing, but we're sharing unequally. One of the atoms in this bond is hogging the electron density. And what if we get to a situation where you and your twin, you like ice cream, your twin hates it, it's a straight up situation where your twin's not going to have any of the ice cream, right? You're taking it all. Because you like it, they don't. There's no reason for them to take any. That's when you have a difference in electronegativity of larger than 1.7, right? So this is a big difference in electronegativity. One atom likes electrons, one atom doesn't like electrons. It's mutually beneficial for one of them to just get rid of their electron and become positive, and one of them to just gain that electron and become negative. That's when you have an ionic bond where we have that transfer of electrons. So with your periodic table of electronegativities, let's go out and let's try the sample problems that you see on your note guide. Again, you should have that periodic table in front of you, and what you want to do is define the electronegativities for these atoms. So you'll notice on your periodic table that sulfur has an electronegativity value of 2.5, and hydrogen has a value of 2.1. And if you're looking at hydrogen and you say, wait a second, that's not 2.1, it has a value of 1.01 beneath it, you're looking at the wrong periodic table. That's its atomic mass. We want its electronegativity. So find a periodic table with electronegativity values on it. What we care about is the difference between these two numbers, so you can either just subtract the smallest one from the biggest one always, or just always take the absolute value. The difference between 2.5 and 2.1 is 0.4. And if you come up to your trusty little chart up here, you'll notice that a difference of 0.4 is in the polar covalent bond category. So this is going to make a polar covalent bond. And I'm just going to write C for covalent. All right, if you want to pause the video and try your own, feel free, and then rejoin us. So once you've rejoined, let's look at lithium and fluorine. Lithium has an electronegativity value of 1.0. Fluorine has an electronegativity value of 4.0. Difference between those is 3.0. That is greater than 1.7, so this is in the ionic category. Potassium and chlorine. Potassium is 0.8. Chlorine is 3.0. That's a difference of 2.2, which is greater than 1.7. So again, we have an ionic bond as the type of bond that would form between those two atoms. Iodine and bromine. Iodine is 2.5. Bromine is 2.8. Difference between those is 0.3. 0.3 is a really small difference. In fact, it's way down in the left-hand box above here. It is in the nonpolar covalence category. And finally, carbon and hydrogen. Carbon has an electronegativity of 2.5. Hydrogen is 2.1, and you would say 0.4, which would be a polar covalent bond, but then you say, wait a second here, I know something, which is that in biology we said hydrocarbons are always nonpolar. What the heck is going on? And so what's going on is that there's a special case. It turns out that even though hydrogen and carbon have this difference, hydrocarbons are always nonpolar. So there's one exception to these rules we're learning, which is that hydrocarbons need to be considered nonpolar covalent, even though they have a slightly larger difference in electronegativity than we would expect. And one final note just to be aware of, you can also predict this broadly using your periodic table. So we know that there is this staircase that separates metals from nonmetals, right? So metals are over here on the left, and nonmetals are over here on the right. And so in general, if you have a metal bonded to a nonmetal, in general that's going to be ionic, and in general two nonmetals bonded together is going to be covalent. But of course you need to check the electronegativity values to know for certain, and You need to check the electronegativity values to know whether it's a polar covalent or a nonpolar covalent, even if you have two nonmetals bonded together.